Hello PCH. So here is a video on parametric functions, or introduction really to. So what is a parameter? Parameter is like, we're going to be looking at, say, a vector or a rocket being launched has horizontal and vertical motion. And you can look at those two different motions separately using a third parameter called time. And it'll have certain properties that we are going to investigate, and allows us to, on the grapher, graph something that is not a function, which will help us look at our inverse trig graphs. So we're going to start off with a basic example where you have, where we have a set of equations. Notice it's x in terms of time, y in terms of time, and time from -2 to 2. So what we're going to do is first fill out this table. So if our time is from -2 to 2, we're going to fill this out with that sequence. And then above, I always like to write my equations, and we're going to then fill out time and come up with a traditional XY coordinates that we can graph. So what do we have here? So if x is -2, that's going to give me 5, plugging in t is -2. If it's -1, that's going to give me 2, then 1, then 2, then 5. For the y value, I'll get -4, -2, 0, 2, and 4. So what we have created here by using that parameter is just your traditional Cartesian XY coordinates, and let's then go ahead and graph them. So we're going to go to the coordinate 5, 1, 2, 3, 4. Here's 5, -4, 1, 2, 3, 4. So that puts me about here. That's where we're starting. Then I'm at 2, -2, then 1, 0, then 2, 2, and 5, 4. And so to represent that motion, we go to where we started and we connect the dots in order. And then I always like to put a little arrow. This is the kind of thing you'll do in calculus. You're showing the path of a particle, its motion, as it is going through time. And that's really all that is right there, is taking our parametric equations, giving it a visual representation in our Cartesian system. And then what we can do is we can actually eliminate the parameter so that we have just an equation in terms of x and y. So let's see how that looks. And if you notice that graph, it kind of looks like way back in the beginning of the year when we did the Boolean algebra and we're able to graph something within a restricted domain. It's kind of what time is doing here, since we're only looking at the path of the particle within a particular span of time. So to eliminate the parameter, I'm going to first write down my two equations that we're working with. So we want something, our goal is to have a final equation that is just in terms of x and y. And so the first thing I do is I like to isolate t, and then I'm going to, in the x equation, and substitute it into the y equation. So x minus 1 equals t squared. And then when I take the square root, we have to put in a plus or minus, and that will equal t. So now I'm going to come down here to my y equation, and we have y equals 2 times what we just simplified. So that's going to be plus or minus 2, because we want to emphasize that it's a product. There is our equation. Now notice that that graph is not a function. It doesn't pass the vertical line test. if I was going to graph it on my grapher, I would need two different equations. This top portion, that would be your y1, and this bottom portion, that would be the negative 2 square root of x minus 1. That would have to be a separate equation in order to graph them on the same axis. And later on, we're going to show how when you do it on the calculator, you can use something called parametric mode, which allows you to graph the whole thing, anything that's just a relation. Now, one of the things, this is going to be a sort of preview of coming attractions because we will be covering conic sections later on. So we're going to use parametric equations to sort of look at one conic that is ellipses. So an ellipse, hopefully you know what an ellipse is, but it looks something like this. So it's like a circle that's been elongated in one direction or another. And notice it's not a function. So it's really nice if you have parametric equations because then you can graph that on your calculator. Now, how do we eliminate the parameter in here? Well, this is going to be one reason why it's attached to this chapter. So I'm going to write down the steps you would go through here. First thing is I would isolate my trig. So right here, I'm going to get x divided by 4 equals cosine t. Here, I'm going to get y divided by 6 equals sine t. So that would be your first step. Second step would be to square everything. I'm just going to abbreviate that. So I'm going to go through and square that, square that, square that, square that, and then that last step is going to be find the sum, I guess, or take the sum. I'm not sure how to say that. So we're going to draw a line here, and I'm going to get x over 4 squared plus y over 6 squared equals cosine squared t plus sine squared t. Hopefully you recognize that this should equal 1, and voila, we have something that just has x and y in it when you make that substitution. Now, what does that really represent? So a conic section, and again, this is just a quick introduction to this, is going to be, if I'm going to graph it, notice that there's nothing added or subtracted to the x or y value. So that means my center of my ellipse is at the origin. The number in the denominator of the x term, that 4, tells me how far I go in the x direction from my center. So I'm going down to -4 and 4. And then I'm going to go up to 6 and -6. And that, I mean, obviously my scale's a little off. It should be bigger on the x in the y direction. But that would be my ellipse. All right, so that's your first little introduction into ellipses. So let's do the second example here, where notice you have a little more going on, but the steps are basically the same. So we want to isolate the trig. So this is going to become x minus 4 divided by 3 equals cosine t. This one's going to be y plus 1 divided by 6 equals sine t. Notice how we're doing the x with the cosine and the y with the sine. Then I'm going to go through and I'm going to square everything. And then we go through and we take the sum. So what I end up with is, you know what, I'm going to do it a little bit differently this time, just so you can see, because I don't really care which way you write it. X minus 4 squared over 9 plus y plus 1 squared over 36 equals cosine squared plus sine squared, which we know to be 1. So then if I had to graph that function, sorry, getting out all my colors here. So we can see, if you think about when you, because you've worked with parabolas before, so x minus 4 and y plus 1, those two terms tell me that my center is going to be, and we call the center, just like we do with a parabola, we call it HK. I seem to have lost my pen. Here's my HK. So in this case, our HK, which is the center of the ellipse, is going to be 4, negative 1. 1, 2, 3, 4, negative 1. So there's my center. And then I'm going to go the square root of 9, which is 3. I'm going to go 3 forward. So that puts me here, and it puts me out at 7. Excuse me. And then the square root of 36 is 6. So once again, that's going to put me up here at 5 and down here at negative 7. And then we just connect the dots. And there's our ellipse. All right. So we will look at also graphing this on the grapher, which has a real advantage, but it's really, we're not going to emphasize using the grapher that much, but you can see how you can eliminate the parameter and come up with a Cartesian. If you want, you can, I never seem to really, but here is the relationship. So in parametric form for an ellipse, x equals h, which is the x coordinate of your center, plus a. A is that distance we went in the x direction from the center. That number, if it's the bigger number of a and b, is going to be half of your major axis. The smaller number of the a and b would be called your minor, or half the minor axis. Yeah, and so that would give you your parametric equations for an ellipse. So here's another example. We have the path of a rocket is modeled by the following parametric equation. So we have our horizontal distance in meters. So I'm going to put that down here. So here's our x in meters. Here's our y, also in meters. And then you have the parameter of time. So plot the graph of the rocket from launch to impact and label the values on your graph. So we're going to label those points. So what do we have? 0, 3, 6, 9, 12. 0, 3, 6, 9, 12. And then we're going to have x equals 20t. So that's going to be 0, 60, 120. Hello. I can multiply. 120. Then we have 180. Then we have 240. On the other side, negative 4t squared plus 48t. So when we plug in our different time, we have 0, 108, 144, goes back to 108, and then this will also give me 0. So these again represent actual XY coordinates that we can go through and graph. There you go. So how is that going to look? We have to figure out a scale. I am going to, now somebody made a nice point on the x direction. I'm going to let my scale be, each one of these is going to be 60. So 120, 180, 240. And I think I did it differently on the written notes, but it doesn't really matter. And then in the y direction, I'm going to do these by 50. So each one of these little things is 10. So 50, 100, 150. So we have the point 0, 0. That one's easy. 60, 108. So 60, 10, since each little thing represents 10, 108 will be about there. Then we have 120 at 144. So here's 140. So 144 will be a little bit above that. Then we have 180, 108. So you have that symmetry going on. And then 240, 0. And again, if I connect those dots, so we started there, and as time is going, each dot represents one of those times. And then I'm going to put my little arrows on here to show the direction that we're traveling in. So the first thing we want to figure out here is when, so we're solving for time, will the rocket be 100 horizontal meters from the launch site? So horizontal is the X direction, and so 100 is here. They want to know at what time are you at this point, because that's when you're 100 meters from the launch site. So horizontal is governed by this equation, and since we're solving for time, that means we plug in 100 for the X, because that's our position. When I solve for time, I get 5 seconds. Whoops. Yeah, 5 seconds. Sorry, I looked at something else. All right, at what 2 times will the rocket be 80 meters high? So 80, 67 is right here. Following that, so here's 80 going up, here's 80 going down, and what we want to find is what is the time when that happens. We do know that this is at now t equals 5, so it makes sense we're going to have something before 5 and something after. So same thing, now we're talking vertical distance, so we're going to use that y equals -4t squared plus 48t, and we're going to then set that y is equal to 80 meters high. So we have a quadratic that we can set equal to 0, so 0 equals -4t squared plus 48t minus 80. I'm going to divide everything by a -4, because I don't like to have a negative out in front. And that is going to give me 0 equals t squared minus 12t plus 20. That is factorable into t minus 10, t minus 2. So my 2 times are going to be at 2 seconds and at 10 seconds. So here's at 2 seconds, and then this would be at 10 seconds. Okay? Now it wants us to write a Cartesian equation. In other words, eliminate your parameter t. So just like before, here's the 2 equations I'm working with. So -4t squared plus 48t. So I always start with the x1 and isolate my t. So x over 20 equals t. And then we substitute that into the y equation. So y is going to equal -4 x over 20 squared plus 48 times x over 20. And please, please do not give me that as your final answer. You want to go through and simplify that. So 20 squared is going to be 400. So this is going to simplify to -4 over 400. The negative will still be there, but 4 over 400 reduces to 1 over 100. And then we have 48 over 20. 4 goes into both of those, so 4 goes into this 12 times, it goes into this 5 times, so plus 12x over 5. That would be eliminating your parameter, just your normal function in terms of x and y. And it's just your normal parabolic behavior, okay? Now, okay. So when we get to this example, we have a senior party pad is 144 meters above the launch site. Now this particular question, unfortunately, we used one of the actual numbers in our table, but we're going to still go through and do the problem as if we don't already know the answer, okay? Because you will get other times when you don't know. So there is a senior party pad up here, 144 meters above the launch site, and the rocket is launched from 120 horizontal meters. So that's down here. And the juniors that's their rocket trying to hit that senior party pad, and we want to know whether it actually hits it. So the way I would work this is I would first start with the fact that I know at a horizontal distance of 120, what time is it hitting that pad? So dividing by 20, I get that t is going to be 6 seconds, which again is still fitting in with all our records of time on here. Now, what is the height at t seconds? So then I go to my y equation, which we have here, and in the y equation, I'm going to plug in the 6 so I can see at 6 seconds, did we hit the right height? I know I have the right horizontal distance, and we do happen to know, since we already did the table of values, that this would give it to us. But later on, you are going to get a problem where you shoot something and you don't know whether it lands before, whether it hits it, or whether it makes it over. So you want to figure out, what is the time it takes you. So if this is like a wall, what's the time it takes you to get to that horizontal distance? And then what is your vertical distance at that time? And then you can determine whether you actually, whatever you have, makes it over the wall or not. Okay? So that's our little intro to parametric. Now, down here, you're going to need a grapher for these. It's a little bit hard to do this through explain everything, but I know there's some things I want to change here. This first problem, you want to do it in radian mode. And on your grapher, you have something called the mode button, and you just scroll down to where you'll see something. It's right below where you'll see radians and degrees. That's how you toggle back and forth. Then you have function. Right next to function, you'll see parametric. And so you want to go through and highlight parametric. As soon as you do that, when you hit your y equals button, you will see this. So you can enter in your functions, x in terms of t and y in terms of t. So you would have here sine t, and then the y1 would be t. And you could set up this window exactly as it's written here. So notice you have a t step. We're doing time from -10 to 10, and then what's happening there. What you're going to end up seeing when you graph that, I'm just trying to remember, 0.1, I'm trying to remember if that's too small. No, I think 0.1 was actually good. What you are going to see when you graph that is your sine function. Whoop. Your inverse sine function, sorry about that. So it's going to snake up and down. So this would be your x and your y axis, which notice it's not a function, and you should be able to see that. Do not worry if this isn't making sense with the graphing, because you don't have to do this as a graph, but it is helpful to know, and that's something when you do return I can show you in person. The second one is same idea, and I wrote these a little wrong, so this would be x1 of t, this is y1 of t. So you're going to enter, let me do this in a different color. So x1 of t will be 4 cosine t, y1 of t is going to be 6 sine t. This one we're going to do in degree mode. This is the one we want to do in degrees. Your window then, so our minimum is 0 degrees, our maximum is 360. In other words, we're going to go once around. Hopefully you recognize this. This is our ellipse. And now the t-step, that's not going to work. Point 1 would take days to graph it. So if you're too small, since degrees are bigger, radians, you know, you go once around, that's 6.28. That's the same as 2 pi. But in degrees, 360, so I would say you could go every 5 degrees. And everything down here could be the same. And so when you go ahead and you graph that, you will find that you'll be out here at 4 and -4, up here at 6, -6, and you should get a graph that looks something like that, which is kind of cool. So that's how you can graph all at one time without separate functions parametrically. Okay?